Good morning, thanks for coming. Today we have a special guest, Adolfo Cisterna. Adolfo is a Chilean physicist who has a huge experience in GR and beyond GR, searching for black hole solutions. He was working in Italy, now in Czech Republic, in Prague. He's going to be with us for a couple of days. And today he's going to talk about anti-de-Sitter Taub-NUT and exact black bounces with the scalar. So,
okay, thank you, Jorge, for the introduction. Thanks to all of you for being here, even if this is basically holidays. And thanks to the university for inviting me. So the idea, this is one long talk that I divided in two because I was asked to give two seminars and one of them with more introduction than the other. So this is it's going to be based on this paper that has been recently published in Fyzikálním Ústavu. And that is, Jorge is saying, is related with some special type of solutions that have been studied during the last time that are called black bounce. So the main idea of this work was to put this sort of proposed metrics into a well-defined action principle and to find this space-time as exact solutions of some field equations. So at the very beginning, I'm just gonna give some super general remarks about black holes in GR, such that at some point we can introduce what the Taub-NUT space-time is, and once we know more about the Taub-NUT, I will tell you about how we are including this scalar curve on this type of space-time. So this is going to be the first half of the seminar, and in the afternoon I will go directly to the new results we have, which is basically this type of solution we have constructed in this setup I'm going to explain now. So the aim of the talk is to present this Taub-NUT solution. Taub-NUT is a particular type of space-time that arises as an exact solution in GR. Okay, so that's just the name. And Tau is not the name is due to the authors that for the first time described this geometry. And the idea of the paper and the idea behind this talk is to present some new Taub-NUT solutions to a well-defined system which is given by GR supplemented by some type of particular scalar field I'm going to show you later. And our aim is going to be the explicit construction of some solutions that are called black bounce and that represents several transitions in between different types of solutions. These solutions are regular black holes, so black holes without a central singularity. You know that usually the most simplest black hole we have, the charged black hole, that is pretty well known, it possesses a central singularity, right? A point in which the curvature of the space-time completely breaks down. So people usually believe that this is a classic problem and that when a quantum gravity theory will be at hand, actually the singularity is not going to be there, it's going to be solved. So many people anyway is looking for black hole solutions which are regular at classical level. So you solve Einstein equation in some setup and you expect that there is no singularity. This type of solutions are called regular black holes. So in this work we will show how these solutions arise and how they can also transit to other solutions, to other geometries that in our case are given by wormholes. So this type of solution that people usually use in science fiction that connect two distant regions of the universe through a throne, let's say. And also some type of solution which is called bouncing cosmologies and that represent cosmological space-time, like solutions of Einstein equations that describe the evolution of the universe, but that instead of having an initial singularity, like the Big Bang singularity, there are solutions that actually bounce and close itself. So the space-time, the universe, let's say, expand, start to close, and go through a minimum value, which is not zero, which is not a singularity, and expand again, and so on and so forth. These are called bouncing cosmologies. And in this work, I will show you how all of these solutions may arise in one closed context and how they transit in between them. So this is the idea. So let me start with the simplest black hole we have at hand, which is called the charged black holes. Of course, if anyone has a doubt about this or at any point in the talk, you can stop me whenever you want. So in 4 dimensions, in general relativity, which is a theory that describes gravity, so basically a theory that tells us that gravity is due to the effect of matter curving the space-time, right? And this theory, which is described by Einstein equations, possess several exact solutions, and the simplest one we have at hand that represents a black hole is the Schwarzschild metric. This is the Schwarzschild metric in Schwarzschild coordinates, so basically you have spherical coordinates, and you solve Einstein equations, and what you get is that the metric of the space-time is given by this line element you have here. Okay, this is the standard black hole solution we all learned at the very beginning. And this solution is interesting, it's spherically symmetric, and it's static, and by Birkhoff's theorem we know it's the only static, spherically symmetric solution we have in Einstein equations in vacuum, so when there's no matter. This is an exterior solution, so there is a body that is spherically symmetric, is static, and outside this body the space-time is described by this metric you see there. And an interesting way to study the Schwarzschild solution is to construct what is called or known as Penrose conformal diagrams, which is let's say a conformal compactification of all the space-time that allow us to describe the geometry of a given solution in a finite diagram. So basically the Schwarzschild solution described by this line element, what this line element is described in this coordinate is this area of the conformal diagram, which is the exterior solution of the Schwarzschild black hole. This is called the Schwarzschild patch, and here you see that the even horizon is given by these two regions, which are the zeros of this term here. This is called the even horizon at r equal to m. Scribe minus and scribe plus represents past and future null infinity, so the places where light rays arrive at the future, infinity future, and the place where they were coming from at the past infinity, null infinity. This point is called the space-like infinity, and I minus and I plus are represented by past and future time-like infinities. So when I am going to infinity in time and when I am going to infinity in the past, these are given by these 2 points. And although this metric only represents this patch here, this area which is in between the infinities and the horizon, the even horizon, we know that by studying this metric in other coordinates, we can extend the study of the full space-time, and we are not only restricted to the coordinates that belong in between the horizon and infinity, but we can go beyond. And when we go beyond by different set of coordinates, which are called Edison Finkelstein coordinates, we do all this study of analyzing the geodesics of observer in this space-time, blah blah and so on. You discover that actually there is much more than only the Schwarzschild patch in this space-time, but there is a mirror space-time which has the same property than this one, something that you discover when you study this metric in isotropic coordinates. Then you realize that no, actually there is a mirror space-time that is connected through something which is called, through a minimum area which is called the Einstein-Rosen bridge. And that not only that, there is also a space-time here, this area which is called the white hole. This is a time reversal version of this metric in which the black hole turns to be a white hole. So things, particles cannot enter, but they only can leave. Okay? And of course, when you cross the even horizon, at some point you catch the central singularity, which in this case is space-like, because remember that once you cross the horizon once, time and space coordinates are inverted, so what is time and radial coordinate here completely change to the opposite when you are inside the black hole. And this is the type of black hole in which then the central singularity is space-like. What it means that once I cross here, I am forced to crash to a singularity and I don't have any other option. Why? Because what it was a coordinate as a space coordinate, like the radial coordinate, now became time. Okay? So, and time is always passing, so I cannot stop it. So basically what I cannot do that once I cross the horizon is I cannot stop moving until I crash the singularity. Okay? Nevertheless, in Einstein theory in vacuum we have more solutions, and the second one we have at hand is obtained by simply taking the Schwarzschild black hole and including some electromagnetic fields. So basically we are solving now the field equations of Einstein-Maxwell theory. So we have a body now in where there is also distributed some electromagnetic field. Okay? If we take a pretty simple electromagnetic field, represented by electric charge and a magnetic monopole, which at this point is only theoretical. We know there are no magnetic monopoles. We are going to talk about magnetic monopoles soon because Taub-NUT is somehow, the Taub-NUT space-time is somehow a gravitational analog of the Dirac monopole, which is basically the theory we have at hand to describe an hypothetic monopolic magnetic charge. So imagine you have a magnet and you carry it in two, so you have north and south pole. Each of these independent pieces of the magnet, in the case you of course divide the magnet and you don't create another magnet. So imagine that you are able to isolate the poles of the magnet. This is what we are going to understand by a magnetic monopole, and the Taub-NUT space-time is a gravitational analogous. Okay? But now let me just go with the Reiner-Nostrom space-time, which is the solution when I have a magnetic electric charge, a monopolic charge, and it will solve Einstein equations in a spherically symmetric static context. What you get is this space-time, which is a little bit different. So you see the line element now is more involved, and now there is more than one horizon, because the solution to this function, to this polynomial R, has two roots. Well, there are several details I am not giving here, but the idea is that now, if you look at the conformal diagram, the Penrose diagram is much more complicated. So now you have something here where you have again null past and future infinities. You have the same in time-like infinities, right? The space-like infinity, which is here, I didn't put it. But now you have two horizons, and these two horizons change completely the structure of this solution. Actually, you are here, which is something pretty similar to the Schwarzschild patch, and is the area of the diagram that is described by these coordinates. At some point, you cross the first horizon. What we know is an even horizon, which is R plus in the diagram. Then you enter in this kind of interior region of the black hole, but then you have a second horizon, which is R minus, and this is called the inner horizon. Okay? Again, this area is time dependent. What was the R coordinate and the time coordinate in this Reiner-Nostrom Schwarzschild patch, now it's exchanged. So here things depends on time. And at some point, you cross again this R minus horizon, and you face now a singularity at R equals 0, but that is not a space-like anymore. Now the singularity is time-like. If you compare with the previous conformal diagram for Schwarzschild, you see the position of the singularity here. The position here is completely different, right? Now this is time-like, it's space-like again. Why? Because once I cross again the horizon R minus, I am changing the nature in between the time and the radial coordinate. So now actually I am not forced to go and cross with the singularity. So now I am in the Reiner-Nostrom patch. I am moving there as I want. I cross one even horizon, and I enter in this time-dependent region, which is what we call the black hole there, in between R plus and R minus, these two horizons. When I am there, I am forced to move, because again, R is a time coordinate, and the time coordinate is a radial coordinate. Once I cross R minus, which is this inner horizon, I restore somehow the nature of my time and radial coordinate, so now actually I can move in my original radial coordinate. So in principle, I am not forced to crush the singularity. And this is important because we see that this diagram actually is infinite. There are infinite copies of this diagram, so infinite patches of this union. And why we are forced to continue is basically because when you analyze in detail how particles move in this space-time, in Reiner-Nostrom, you can understand that actually here there is a potential barrier that once a particle crosses R minus, this particle approaching R0 feels a negative potential that expulses the particle again. So actually, if I am a particle and I am moving inside and I actually want to go to the singularity with a rocket or whatever, I cannot, because there is a turning point there that sends me away again. But I cannot go back to this horizon. Why? Because actually you see that this horizon represents a line in 45 degrees. So actually, if I want to cross back the same horizon R minus I cross to enter the central region, I should go faster than the speed of light, and I cannot. But actually, this other horizon here, I can clearly cross this one. This one is not in 45 degrees, right? So in the same way I cross R plus here, I can continue and cross this second, let's say, R minus horizon I have there. And what that is, by being forced to move from at 0 and crossing R minus again is actually what is telling me that I am going to another universe again that is a copy of the first one, and I am forced to go there. Okay? And this area here, again, in between this R minus and R plus, this area here is a time reversal version of this black hole. So basically, I am forced to go through the white hole. So then I am in the white hole, and in the white hole, the only chance I have is to leave the white hole, because that's why it's a white hole, right? So I am moving out from the white hole, and I cross this, again, R plus horizon, which is a copy of the initial one, my even horizon. And when I cross R plus, which of course I can do it because if you see, I am inside, so I don't need to go faster than the speed of light to cross this horizon. I cross the horizon, and I am again in a radial nostrum patch. So I am again in another universe with the same characteristic of the initial one. Which is the difference? That, as I told you, for some reasons that we don't have time to investigate here, there is another turning point now, as the one we have in this region, that tells me that once I leave when I am leaving the white hole here, I will face now in the radial nostrum patch another turning point that is going to send me back to cross this even horizon. And then the process is going to repeat itself ad infinitum. So that's why actually this Penrose diagram is composed by an infinite number of universes that repeat itself in both directions. Okay? So this is what is going to happen with the radial nostrum black hole. There are small subtleties depending on the relation in between charge and mass. So for example, we know that here, if I solve the horizon, I have two horizons, and these horizons depends on a square root. Inside this square root, there is the mass and the charge. I didn't put the form of the horizons there. We talk now, what I said is valid for the known extremal solution. It means that both horizons exist because the mass satisfies some condition and is greater than some value related with the electric charge. So when the mass is greater to the electric charge by some factor, we are in the non-extremal solutions, and this is the diagram, the Penrose diagram that applies. And what I said is valid when there is a particular bound that is satisfying between the mass and the charge, which is called ordinarily charged particle. When particles have, let's say, enough mass in comparing with the charge, the particles follow precisely what I said. They are forced to move and to satisfy this and to go through these turning points in these regions I show you. Okay? There is the case in which the particles are extremely charged, or when they are overcharged. In the case when they are overcharged, there is a possibility to skip this turning point here, and actually, in principle, the particle could hit the singularity. Okay? But it's a more exotic case. Well, this is the conformal diagram of the non-extremal solution, and what I said applies for the ordinarily charged particle. Okay? But we can move now away from spherical symmetric and static solutions, and we can move to a stationary spacetime. Okay? So the difference in between a static and a spacetime, basically both concepts are telling us, okay, the metric coefficients, they do not depend on time. Okay? So if you see all these metric coefficients I have written here, in this metric I'm going to tell you what it is, but also in the radial nostrum and in the Schwarzschild, they do not depend on time. Okay? This is a condition that is required for a metric to be static and stationary. But the staticity is much stronger condition than stationarity. Okay? And staticity also implies that the metric is a hypersurface orthogonal. That depends, it's a more mathematical concept, but it says that the metric do not depend on time, so there is some symmetry related with time translations. And this symmetry, mathematically, is represented by the existence of a time-like killing vector. Okay? So every time I have a symmetry, there is a time killing vector, and this time killing vector arises because actually my metric components do not depend in the coordinate. So this metric do not depend on time. There is a killing vector which is time-like. They do not depend on the azimuthal angle phi. There is also a time-like, space-like killing vector associated with this symmetry. Okay? Stationarity simply implies that this time-like killing vector exists, so the metric do not depend on time, but staticity also tells me that this time killing vector needs to be surface orthogonal. Okay? This is a mathematical condition. Now, stationarity in space-time, where this hypersurface orthogonality is not being satisfied, the most general and actually the unique stationary axially symmetric solution of Einstein equations is known as the Kerr black hole, or the Kerr metric. And the Kerr metric represents the exterior region of a body that now is also rotating. Okay? This is the Kerr metric. It's much more complicated, and its structure is much more involved too, but much more interesting, and do possess also two horizons, the outer or even horizon and an inner horizon, just as we saw in the Rayleigh-Nostrom case, but it also includes two new effects due to this non-diagonal term that you see here, which is actually called the lens-theory non-diagonal term, this term in the metric. It includes something which is called the ergosphere, or usually it's called the ergosphere. And this is a particular surface which do not coincide everywhere with the inner horizon, and there is a surface, a region in which once you are there, you cannot stay in your position in this space-time. So it's a kind of stationary limit. So when I am approaching the black hole, before facing these horizons I am telling you that are in the Kerr metric, you first the outer ergosphere boundary, and in this boundary, as well as in the inner one, you cannot stay still at your place. So you are forced to rotate with the black hole. And many interesting things are happening because of the presence of the ergo region in the Kerr black hole in comparison with the Schwarzschild or the Rayleigh-Nostrom and other static solutions. So the ergo region is something, is a novelty incorporated by stationarity basically, because it depends completely on the presence of this term. So as soon as I kill this parameter A that is related with the rotation, the ergosphere doesn't exist anymore. And there are several things that happens because of the ergosphere. Some of them is called the Penrose process, which allow me to extract energy from the black hole, because actually in the ergo region here, the time-like killing vector dt becomes a space-like, and there are some things that are happening there, and you can extract energy and so on and so forth, but we are not going to enter into details. Moreover, if you see now, this here, or this ring, represent now the singularity. So the singularity is not at only r equals 0, but it's r equals 0 and theta equal pi over 2. So actually it's a ring. The singularity changed completely. But this is happening with the Kerr metric. And the other new effect, which is related with the rotation, is called frame dragging, and can be understood by this picture. Is basically that if I am at infinity and I drop a particle there with zero angular momentum, okay? So this particle has zero angular momentum, and I drop it falling down into the space-time. The space-time itself is going to drag the particle, and the particle is going to acquire an angular velocity, no matter it started with zero angular momentum. So I will have non-trivial angular velocity, but with zero angular momentum, okay? And this is something which is exclusively related with the fact that the metric now is stationary. Okay, this is called the frame dragging effect, and it actually can be measured. So basically, it's called dragging because the body that is rotating is dragging with itself the space-time around. And you can compute this even for Earth. So Earth is rotating and is dragging things around the space-time. Okay? Now, besides these solutions, in GR there are other two solutions that are also included in a super general family of solutions I'm going to show you now, which are called the symmetric and the Taub-NUT space-time. And these two spacetimes are a little bit different because somehow they have some topological defects there. So they are not precisely, let's say, regular in the same way that the Kerr and the Schwarzschild and the Rayleigh-Nostrom black holes are. One of them, the symmetric, represents a black hole, or actually two black holes, that are accelerating. So black holes with acceleration. And actually, if you take, this is the symmetric line element, if you take the limit in which you try to go to Minkowski, you actually arrive to Rindler space-time.
Oh, it's linear acceleration.
Yeah, yeah. No, there's not rotating. So basically, you arrive to Rindler. Which is Rindler? Rindler is how an observer that is accelerating see Minkowski space-time, right? So when you are in Minkowski, let's say, at rest, but then you start accelerating with constant acceleration, okay, in a rocket. And then you, from your reference frame, you try to describe the metric space-time. What you are going to see is a space-time which is called Rindler. Because 2 actually is pretty similar to this. Of course, forget about the singularity, blah, blah. But you will see that a guy that is seeing Minkowski space-time, if you may infer, looks pretty similar to this area of the Schwarzschild patch, right? Because the Schwarzschild metric is asymptotically flat. So when I am going to infinity, what I have is Minkowski. Then of course in Minkowski you don't have any horizon. So actually if you compute the Penrose diagram of Minkowski, you are going to find this diagonal here, no? But these are not horizons, of course. But when you are accelerating with constant acceleration, your space-time now is seen in a different way, and 2 horizons appear. But these are accelerations horizons. These are horizons that, as soon as you stop moving in an accelerated way, they do not appear anymore. So basically, the Rindler space-time is a patch of the full Minkowski space-time. Okay? So the symmetric, what represents is precisely the space-time of a black hole that is accelerating, where this alpha parameter here I have included is this acceleration. Okay? And how people understand this acceleration? They understand it because this metric, which is static but it's not spherically symmetric anymore, because if you see here on the d theta component there is a factor, there is a function of theta, this factor here that depends on the acceleration. So as soon as I kill the acceleration, I don't have this problem anymore. In here there is a kind of conical singularity, some defect in the space-time that I am trying to represent here by this point. And it is understood that here this defect acts as a kind of a string or a straw that is pulling my black hole all the way up to infinity. And because of this defect that you can represent that this is a straw, actually you understand this black hole is accelerating by the effect of this defect here at theta equal pi. If you analyze the full analytic extension of this space-time, you actually find that there are 2 black holes that are accelerating from each other, and they are being pulled all the way up to infinity by these straps. Okay? This is the symmetric space-time, or space-time with acceleration. And there is one more space-time which also has some particular properties related with these topological things, which is called the Taub-NUT and space-time, and it's the space-time which we are going to focus on. Well, I'm going to give you all the details of the space-time in a few slides more, so I'm not going to enter now. All these black holes I have told you, the Schwarzschild black hole, the radial nostrum, Kepler, the symmetric and the Taub-NUT, all of them are englobed in one family, which is the most general family of black holes you find in GR, which is called the Deviansky family, and it's the most general family of, in terms of the Petrov algebraic classification of space-time, the most general family of type D black holes, which are some black holes that possess some particular mathematical properties related with the classification of the Bayes tensor. And this metric, which is called the Deviansky metric, is given by this line element. So, if I want to solve in full generality a metric of the type D family in Einstein gravity, and to find therefore all black holes contained in GR in vacuum, what I'm going to find is this metric, which is called the Deviansky family, and that includes, of course, Schwarzschild, which is the static spherically symmetric solution. I can include charge, so I will find the charge version of the radial nostrum. I can now include stationarity, so I will find also Kerr or Kerr-Newman, which are rotating or rotating uncharged black holes. And I will be also able to include acceleration and Taub-NUT parameter, okay? Which is the parameter that controls this solution I'm going to tell you soon about. All these black holes are contained in the Deviansky family. And this is a pretty new form of the metric that was proposed last year by Professor Professor Podolsky in Prague, where they were with some colleagues, they were able to write down the Blavatsky-Viviansky family in such a way that the horizon is pretty clear. So the horizons contained in this metric are given by these two expressions here, and they are easily obtained in terms of the mass, the NUT parameter L, the rotation, and the electric and magnetic monobolic charge. Okay? And this is the Blavatsky-Viviansky family that somehow close a little bit the picture of black holes in GR in vacuum. Of course, you can include cosmological constant, and when you include cosmological constant, this can be extended to that case, so there is a Blavatsky-Viviansky solution in de Sitter and in anti-de Sitter. Then, in GR, in vacuum, there are several other solutions, but that are not contained in this family, which represent black holes or solutions that are not radiating. So all of these solutions, they do not radiate any kind of gravitational waves. Okay? Okay, so this is the Taub-NUT, the Blavatsky-Viviansky family. So now let me focus on the Taub-NUT spacetime, which is the type of solutions we are going to talk about more because it's related with our work, with what we did in this so-called black bounce spacetimes. So the Taub-NUT, which is due to Taub, Newman, Tamburino, and Unti, these three first, Taub did first some works alone, and then Newman, Tamburino, and Unti rediscovered the spacetime in a different context. They realized they were studying the same geometry at the end. This geometry is an exact solution of Einstein gravity. So again, the theory we have been talking about since the beginning, which is given by this equation, so the Einstein tensor basically. And it corresponds to the first stationary generalization of charge. I told you that Kerr is the mother of the stationary solutions of GR. But the first stationary metric you can construct, the simplest one, let's say in terms of the metric only, not in the properties or anything else, is actually a Taub-NUT metric that contains a non-stationary term if you expand this square here, right? So you have a d-phi term. So this is the first one, and it's of course a non-radiating solution because it belongs to the petrotide solution represented by the Blavatsky-Viviansky family. And besides the mass, m, the spacetime also includes one additional parameter which is continuous and which is called the NUT charge. Okay? And we will see that this NUT charge here, this parameter n, is pretty much analogous to a kind of magnetic monopole charge. So when we will be analyzing the Dirac monopole, we will see that actually n is a kind of magnetic version of this mass m in gravitational terms. Okay? So m, if I make a comparison in between this spacetime and what I told you at the very beginning about this spacetime being related with monopoles and with the Dirac monopole, etc., I will say in gravitational terms this is called electric mass and NUT is called a magnetic mass. In the same sense, you can have an electric charge and a magnetic charge if you are allowing yourself to study monopolic magnetic configuration. The metric can be written in this way, in this sort of isotropic coordinates, where now instead of using f and using this term here, cosine of theta, I am. Is a question? No? Sorry. Now I have used this other metric function nu, which is basically a reparameterization of this function I have written here. And A is giving me this term here, and I can write this in isotropic coordinates. And actually, if you compute the movement of a particle in a radial geodesics in this spacetime, you will find that the acceleration, the radial acceleration of this particle, follows this equation, where nu, this metric function, gives this vector once you apply the gradient, and where this A gives another vector when I apply the curl. And if you see, this equation, what is representing is basically the movement of a particle under an electric and magnetic field. So it's a kind of Lorentz force law, no? You have this kind of electric field here, magnetic field. This is the speed of the particle. So basically, what a particle moving a radial geodesic in this space-time is describing is basically the movement under an electric and a magnetic field, where this electric and this magnetic field are precisely given in terms of my original metric functions, nu and A, and how they are related. Precisely in the same way, you compute the electric field coming from an electric potential, and your magnetic field coming from a vector potential. Hey.
Yeah, I will ask, who is producing this electric field and magnetic field?
The metric itself. That's the point. Here,
So there is a charge there producing.
no, here there is no charge. That's precisely the idea. So you have the
It's like an
space-time.
equivalent to, okay.
Yes, it's
yeah,
the equivalent
like a kind of electric field associated to this new charge.
Exactly. So you have this space-time, which is called the NUT, and you have only mass and this NUT charge.
There, okay.
Mass and NUT charge, these two new parameters. And just by simply investigating a little bit the radial geodesic, you see that a particle moving in a radial geodesic will follow this equation,
So it's kind of
where E and B are just two terms that arise in this equation. But actually these two terms are related with these metric functions in this pretty suggestive way. And this is telling you, look, these two metric functions that are part of the space-time, this is gravitational setup, pretty much behave as electric and magnetic fields. And that's the point. So people start interpreting Taub-NUT as a gravitational diode with electric mass M and magnetic charge M. Okay? And the NUT parameter, actually, when you are working in the space-time, you start working with the charges and you say, okay, I'm going to compute the mass. I would like to obtain also the NUT charge. You see that the mass, usually you can compute it by using a Komar integral. Some Komar integral give you the mass. But then if you define a kind of a dual Komar integral, in the same way you compute, for example, the electric charge with some integral, and then with the dual of this integral you compute the magnetic charge, and you know that there is a duality between electric and magnetic charge, right? If you do the same in this gravitational setup and you compute the mass, but then you decide to compute something which is the dual of my mass, what you get is actually the NUT charge. So this again somehow confirms that this NUT charge represents some kind of dual of the mass charge. In the same way, 10 minutes more. Oof. Then I have this 10 minutes, no. You have the NUT charge, the magnetic charge is the dual of the electric charge. So there is again some relation there, right? And of course, if you take the limit in which the NUT charge goes to zero, what you recover at the end is the charge resolution. Moreover, this metric implies several other properties. It's not asymptotically flat anymore, because you see that actually if you take the asymptotic limit in your radial coordinate of the GT phi component, this is not going to zero, like in normal asymptotically flat space-time. So there is something that somehow deviates from the behavior of the rest of the solutions of the Jansky family. Again, in this case, the space-time actually is free of curvature singularities. So remember that here, for example, the Penrose diagrams I show you, the radial nostrum has a singularity at r equals 0, and the same for Churchill. And if you go to Kerr, you have the ring, right? And if you go to the symmetric, you also have a singularity. But in the case of the Taub-NUT, your metric is completely free of singularities. It's completely regular in terms of curvature singularity. What it means, curvature singularity, a point in which scalars constructed with your curvature tensor blows up, right? So basically, because of that, actually in the space-time of Taub-NUT, the radial coordinate can take any value in between minus infinity and plus infinity, and it's not restricted to 0 from infinity, because there is no central singularity there. And this is important because, as I told you at the beginning, the idea here is to construct some kind of regular black holes. So I would like to be in a space-time that has some tendencies to avoid the presence of singularity. So Taub-NUT seems to be a good idea. Now the event horizons, it has two horizons that I put here, so R plus minus, and the space-time is stationary outside the R plus horizon and beyond the R minus, and in between R minus and R plus, pretty much the same as we saw in the radial nostrum. In the middle, the solution, the space-time is actually of cosmological type, no? Things depends on time and not on R. The regions that are stationary, so when the metric is not dependent on time, which are these two regions, are called NUT, and the region in between the horizon, which is the time-dependent region, is called the Tau region. Because actually Tau discovered this space-time as a cosmological solution. He was describing precisely the region in between these two horizons. But now, this space-time is a little bit pathological. This is these are two, let's say, less nice features of this space-time. There are two problematic properties or features of this space-time. There are the following. First of all, the cross term n cosine of theta that appears in the stationary term, let's say, what will be the analog of the length theory term in the curve metric, induce a pathological axis, because actually if I go to theta equals 0 or to theta equal pi, I see that on the axis of this axially symmetric solution, the metric takes different values. How can I say that? How can I see that? I just go back to the Taub-NUT metric and I plug 0 here in theta and pi. And I will get that in 0 the value is 1, but in pi is -1. So if I move all over my axis of symmetry, which is theta equals 0 and theta equal pi, right? So the north axis is when I am in theta equals 0, and my south axis when I am theta equal pi. If I go through my axis, I will have two different values. I will have 1 and -1. And actually there is not even a gradient of values changing in between them. It's directly, let's say, there is a step there, no? It's not continuous. This induces a pathological thing there, a pathological defect there, okay? And this is called the problem, this is called the Misner string problem, and it's pretty much related with the Dirac string that appears in the magnetic monopole that I'm going to show you later. So, by analyzing actually this geometry for an arbitrary base manifold, that implies that this two-dimensional section of your space-time here that I put as a two-sphere might be also a plane or a torus or might be an hyperboloid, okay? Depending if this guy has positive curvature, a sphere, zero curvature of the plane, negative curvature of the hyperboloid. So in that most general case, if you compute the gradient of your time coordinate, you get these three things, these three possibilities according for the sphere, for the plane, for the hyperboloid. And you see that at least, well, by doing this change of coordinate, you can get rid of one of these conflicted points. After doing that, you will always have a problem at theta equal pi for the spherical case. So you will always have this problematic axis in the Taub-NUT spacetime. Okay, so this is the first thing. There is a topological issue with the axis in the Taub-NUT spacetime. But moreover, if you compute now the G55 component of the metric, it's not only the last piece of the G55 part of the metric, but it also contains this term. Why? Because there is a defined term here, no? So I collect all defined terms. I have this defined term here inside this sphere, but I have also this one that appears when I expand this metric and I collect the 5 components, no? And you see that the 5 components now has a problem. It has this minus sign here. And what it implies? It implies that in principle, the G55 components of your metric might be negative, right? And this is a problem. Why? Because this is a space-like coordinate that somehow can turn into be time-like by going in some space of parameters in which this is greater than this piece. But we also know that the azimuthal angle is identified in between 0 and 2 pi because it's this angle, right, that goes from 0 to 2 pi. If now this is time-like, this is going to imply the existence of a closed time-like curve, because now if this is negative, this is going to be time-like, but anyway I'm going from 0 to 2 pi in this time-like coordinate, so I will close a circle in the time coordinate, and we know that it's not nice to have closed time-like curves. So this is a second issue that this metric also have, and that is important to analyze if it can be solved. Okay? In the original Taub-NUT metric with the spherical horizon, with the two spheres in the base manifold, there is no way to completely get away from the Misner string or this topological definity axis, nor the closed time-like curve. So the space-time is pretty pathological in that sense. When you include cosmological constant, a few things changes, and as we're going to see, if you include also scalar fields and you look for solutions with other fields going around in the Taub-NUT space-time, some of these issues can be solved, and that's what we are going to see also in the second part of this lecture. So let me finish. If you give me 5 to something else, a little bit more, 5 maybe, I will show you which are the tricks, for example, that people used back then when this space-time started to be analyzed to solve the Misner string, okay? To solve this string, which is what's called Misner string after Misner tried to solve actually the string. So, Misner basically follow a pretty analogous strategy that the one Dirac followed to construct the vector field of the vector potential of a magnetic monopole. I'm going to tell you later on how he tried to find this vector potential for a magnetic monopole. So now just let me refer to the fact that Misner used these techniques to try to solve the Misner string issue, okay? The string in the axis of the Taub-NUT solution. So what he did is that he said, okay, let us take two different patches of coordinates, okay, that he defined as T plus and T minus, and they are related, these T plus and T minus coordinate are related with the original time coordinate by a term that is related with the NUT charge and the azimuthal angle, okay? So he said, okay, let me have, instead of only one time coordinate that is covering the full Taub-NUT patch, let me have two now, okay? And these two, defined by these expressions you see here, they cover the north and the south pole of the axis, so they go from 0 to P over 2, and then from P over 2 to pi. And he said, okay, let me write the metric in such a way that I use this first patch here, which is called the north pole patch, the plus patch, and let me write down the metric in these coordinates, okay? So basically change the time by T plus and write down the metric again. But then you see that by doing this, and by allowing the time coordinate to move in between the values that actually Misner assigned to this patch, you are skipping somehow for an observer to hit this topological axis. Why? Because he said, okay, let me use the coordinates that are covering the north pole. But when I am in those coordinates are not anymore singular in theta equals 0, which is actually this kind of singularity in the north pole. They are only singular in theta equal pi, which is the south pole. And then when you use the other patch, so when you are in the south pole, according to the coordinates, this singularity appears in the north pole, because the values allowed in the south pole are completely regular there, and the value that was problematic was sent down to the south pole. So when you are in the north pole patch, and you expect to have a problem at theta equals 0, actually theta equals 0 is not there, because your coordinates are from theta equal pi over 2 to pi. And when you are in the south pole and you have a problem in pi, actually pi is not there again. It's pi 0, but there is no problem. So basically what Misner did was to punch away the singularity. So an observer moving in the north patch see that there is no problem. The problem was sent to the south pole, but I don't care because I don't have access to the south pole because my coordinates cover only the north one. And when I'm in the south, I have the same issue. It's the same thing. This is called the Misner trick, and this is how he actually solved partially the issue of having a conflictive access there. Okay. But you have a problem because in the equator, where both patches somehow overlap. Well, okay, I'm going back to this one. In the equator, what happens is that both coordinates are related. The T plus and the T minus, they get related. And how they get related? By this expression here. So if you take T from the north pole, T in the south, you make them to be equal, and you solve T plus in terms of T minus, you get this expression, and they are related by 4 times the NUT charge the angle. But this angle is again identified in between 0 to pi. And what implies that? That also your time coordinate gets identified. So your time coordinates again close itself. So you have again closed time-like curves. So you solve somehow the Misner string, but you put closed time-like curves in your space-time. Okay? So that's why usually the metric of Taub-NUT is actually not studied in the Lorentzian signature, but in the Euclidean one, and is mostly used to describe gravitational instantons instead of Lorentzian solutions. So more than black hole, people in Taub-NUT, what they do is that they work in instantons, okay? Solutions to Euclidean Einstein field equations that are useful in the context of quantum gravity and instantons and these kind of things. Gravitational instantons are called, okay? So what I was explaining you before about how Misner solved the Misner string issue is precisely described in this picture. So this is your Taub-NUT space-time, and you haven't performed any change of coordinates. So far you didn't do this, okay? And let's call this 2 and phi C. Let's call it C. When C is equal to 0, when I didn't make any change, I have north and south pole pathological axes. I cannot get rid of them. When I say that C is equal to -1, I solve the one in the north pole. It doesn't appear in the north pole, and I am in those coordinates, but it appears in the south pole, but I don't care because actually I am here. So I am moving in the north pole, and I have sent the singular point to the south. And when I do C equal to 1, I am precisely doing the same, but now everything is pathological in the north one, and everything is okay in the south. So this is more or less the thing. The problem is that you have included a period for the time coordinate, and moreover, the analytically extended Taub-NUT space-time has also some pathologic, so it's either geodesically incomplete or can be maximally extended but to a space-time without Hausdorff topology. What implies that there is no Hausdorff topology implies that you cannot define in a point a neighborhood of a point. So Hausdorff topology tells me that my topological space-time I can always move in between 2 points and divide this point infinite times. So I can be as close as I want, and always can I define my own neighborhood on a point in a manifold. So actually it's what allows me to define manifolds, and on manifolds we want to define tensors and all the machinery of differential geometry. So without Hausdorff topology I cannot do that. So that's why it's so pathological that this is not extendable to a Hausdorff manifold. And well, I could close if you give me 2 slides with what the magnetic monopole is, the Dirac magnetic monopole, and I can close here, and when I am coming back, I continue with what is actually our work. So just to go further in the analogy with Taub-NUT, let me tell you about the magnetic monopole, and we close there. So basically we know that Maxwell equations, the Gauss law, the magnetic Gauss law of Maxwell equations is telling to me that the divergence of the magnetic field is equal to 0, right? So I have a magnet. This magnet is sending away field lines, and when I take them and I integrate them on a closed surface, the total flux, the net flux of these lines is 0, because actually the lines leave my surface but they close back again, because lines that are leaving my magnet in the north pole and enter back again in the south pole. So the net flux in this surface is 0. This is, by applying Gauss' theorem, equivalent to say that the divergence of this vector field is 0. This is Gauss' magnetic law. And therefore, it implies that there are no magnetic monopoles included in the theory, because if I take the same equation, the Gauss electric law, actually the divergence of the electric field is proportional to the density of electric charge, right? And the flux of electric field in a closed surface is proportional to the electric charge. Okay, so this is why I know, or we know, that there are no magnetic monopoles besides the fact that nobody has observed them, right? But let us consider a simple modification in which actually there is a magnetic monopole. So in my Gauss law, I'm going to include a density of magnetic charge that I call rho m, okay? Well, this immediately introduces 2 problems. The first one is that if I then apply the divergence on the Faraday law, I will get that the derivative in time of this magnetic charge is equal to 0. So I am fixing the magnetic charge to be constant always. And this is a problem if the universe is evolving somehow, no? This is the first one. But more important, this equation, in this form, is telling us that this magnetic field can be written in terms of a vector potential. So it's actually the rotor of this vector A. And we know that this vector A, coming from here, is the essential ingredients of gauge theories. And gauge theories are what we use to describe electrodynamics and nuclear forces. So it's pretty fundamental to have the notion of gauge field and gauge theories. So it's problematic because of these 2 things. But nevertheless, Dirac anyway forced the inclusion of magnetic monopoles and try to understand, okay, how can I still have a vector potential for magnetic monopoles and to try to make that theory consistent anyway. So what he did is, okay, let us take a magnetic monopole, so a magnetic charge QM. So I cut a magnet and I have an isolated either north or south poles. How is going to be the electric field of such a magnetic configuration? It's going to be simply like a Coulombian force, no? Like the electric one. So it's going to follow this Coulombian thing. And then if I apply on this B my Gauss law, what I would going to obtain is this magnetic density charge of a point particle, no? So it's going to be the magnetic charge, a single magnetic charge times this delta, this Dirac delta, such that when I integrate in a surface, what I obtain is the magnetic charge. But nevertheless, we have this problem. We know that if I take the divergence of this magnetic field, but this magnetic field is given in terms of a vector potential, this is going to be 0. So how can I try to obtain anyway a non-trivial vector potential for a configuration in which this is not 0? So that's my problem. So how can I obtain anyway a vector potential from a vector potential that will describe my magnetic field? Okay, I know that the vector potential exists because of this Gauss law, which is equal to 0. Let us try to find this potential anyway and to see if I can find a modified version of this Gauss law that is actually proportional to some density of magnetic charge. So what Dirac understood, that to do this, you don't need to consider a gauge field that is globally well defined all over the space. You only need this gauge field, this vector A, to satisfy the mathematical criteria that a connection in the language of gauge theories need to satisfy. Okay? And this criteria is less restrictive. Sorry. So actually, you want to cover the full, let's say, R3 space-time, three-dimensional space-time, minus the origin, because I know in the origin there is a problem because it's the charge, right? So in the origin is my charge. It's okay. You know that in the origin here you need to put a delta, right? So I want to describe the full three-dimensional space-time minus the origin, but instead of having only one well-defined vector potential here, Dirac understood that this was good enough to have two different charges on this space-time and to cover my fullest three-dimensional space with two different vector potentials that you can call A1 and A2. And actually you can do that and you can integrate the field equation for a magnetic monopole and to obtain two vector potentials, A1 and A2, that cover two different poles of my space-time, like precisely I was telling to you before, the north and the south pole in the Misner's trick. And these two potentials reproduce effectively the magnetic field of a monopole. The only thing is that they are not globally well defined everywhere, because if you see here, you have a problem again. So you have problems in 0 and pi once again. So that's why I was telling to you that the Misner's trick to solve the Misner's string situation in Taub-NUT space-time is in completely and in full analogy with what Dirac did. So then these two gauge field A2 and A1, they are related by gauge transformations, and if you ask this function in the gauge transformation to be single value, I'm finishing now. What you get is that the electric charge must be quantized in terms of the magnetic charge, and this is the famous quantization rule of Dirac. So Dirac said, okay, well I have a way to justify the quantization of the electric charge. How? By proposing the existence of magnetic monopoles. If magnetic monopoles exist, through the existence of these vector potentials, I will see that in order to have a well-defined gauge transformations, this condition here, so asking this function alpha to be single value, I will naturally imply that the electric and the magnetic charge need to be related. How is that? Well, and he was analyzing actually how a charged particle will move in the presence of magnetic monopoles, and he was analyzing this from a quantum mechanics point of view. In that quantum mechanic point of view, he understood that the electric and magnetic charge need to be related, and the electric one gets quantized in terms of the magnetic one, if the magnetic monopole exists. Okay? And this, as you see, is pretty much the same that we were discussing before, but for the Taub-NUT space-time in a completely different setup, which is a gravitational one. So, when I'm coming back, I will talk about another strategy which diverges from Mr. one to solve the problems in the Taub-NUT space-time, and based on this one, which is called the modal interpretation, we are going to continue describing the solutions we want to study in the afternoon. So, that's it. Thank you.